I'm very happy to introduce Basak Gurel from the University of Central Florida, and she's going to talk to us about towards Hofer-Zehnder and multiplicity conjectures for dynamically convex Reeb flows.
Thank you. Thanks for having me. So I'm actually connected via my iPad, so I won't be looking at your faces much probably, unfortunately. Okay, thanks for having me. It's my pleasure to talk about this work joined with Erman Chinin and Victor Ginsburg. And so let me get to the setting and the question. Okay, so we're going to be interested in Reeb flows on the everyone's favorite standard contact sphere. So the topology of the sphere is fixed here. So in other words, we're looking at Reeb flows on the boundary of star-shaped domains. And to set the notation, prime orbits throughout the talk, I'll denote them by this circle on top. They will be sort of all over the place. And a few more notation, obviously, I'll have to introduce a bit later. So the topic of the talk is this set, exactly how the set of prime periodic orbits of Reeb flows. So prime in the sense of simple or uniterated orbits. Of course, this is, I mean, you can ask a lot of questions about these things. So the main thing is the multiplicity problem for prime orbits. Again, to emphasize, we are going to be specifically in higher dimensions. Again, not to say that what I say won't be true in dimension 3, but it's just not interesting given that we know essentially everything in dimension 3. And so you can ask whether this set is finite, infinite, when is it finite? Is there a threshold number after which this you have infinitely many prime orbits? And then you can incorporate the type of orbits into the picture. For example, could it be that it is infinite in the presence of a specific type of orbit? Or you can ask if you have an elliptic orbit, hyperbolic orbit, when it is finite, etc. So, and a lot of people asked, of course, these questions. So as a question, this is fairly old, goes all the way back to the work of Lyapunov, of course, Mozart, Rabinowitz, Weinstein, Hofer, Zehnder, Ekeland, lots of people. And here is like a conjecture. Again, conjecture is not new either. It's just pretty much the way it is stated is more or less to give you the idea. I mean, it's a good way to split this question into precisely these two pieces, it feels at this moment, based on what we know. So the conjecture is that, so the n on infinity. One piece of it concerns the multiplicity, as we call it, and I will be on and off refer to it as CM, is that the number of prime closed orbits is at least n. Again, we are on the standard contact sphere to n-1 dimension. And then there is what became known as the Hofer-Zehnder conjecture by now. And then, of course, we know it in the Hamiltonian case, but now we can also state a similar thing in the Reeb case, which is the case I'm interested in here. Namely that if you have more than n, then you have infinitely many. So, the reason why we kind of split this into two is mainly, again, we know a lot more in one case and almost nothing, very little in the second case. So the multiplicity part, as I said, is the much more studied part, and we're going to look at some results, all the results a bit later. It goes back to the work of Ekeland in the 90s, at least for the convex hypersurfaces. And then, as I said, the second part can be thought of as a higher dimensional Frank's theorem for S2, with, again, or in the Hamiltonian case, or the Hofer-Zehnder conjecture, contact Hofer-Zehnder conjecture. So a few things. Well, if I'm going to talk about multiplicity to begin with, it would be good to know that there is at least one. And so in the star-shaped case, this goes back to Rabinowitz, 79. So we have at least one prime closed orbit. And before this, this was proved for convex hypersurfaces by Weinstein. And then, of course, we know Viterbo proved the Weinstein conjecture for this sphere. So we know that this is the case for all contact type hypersurfaces. So what else? So in the multiplicity result, the number n or infinity, of course, comes from somewhere. We know that non-degenerate replows on irrational ellipsoids have exactly n prime closed orbits. And then another way to phrase the Hoffer-Zehnder conjecture would be that if you have finitely many prime closed orbits, then you have precisely n. So there is a point to phrasing it this way, because as we will see later on, the proofs are pretty much work. In the case of our proofs, I always assume that we have a pseudo rotation. So let me also take this opportunity to set this terminology here. When I say pseudo rotation, I will mean that a Reeb flow with finitely many prime closed orbits. So in higher dimensions, the key thing is that beyond the Weinstein conjecture, we know essentially nothing. So very, very little in the generality that I've written. For instance, do you have more than one? So if you don't assume anything, like some index condition or like convexity, dynamical convexity nowadays, or some non-degeneracy, we don't know if you have at least two, for example. So it is in the generality I wrote, it's a fairly open question. So this brings me to, before I can state the results, the conditions that are sort of commonly imposed in the kind of in this kind of question. So this is dynamical convexity. So dynamical convexity, this assumption goes back to the work of Hoffer, Wysowski, and Zehnder, and it is a lower bound on indices, on Conley-Zehnder indices, or in the non-degenerate case, or more generally the mu minus. This would be the lower semi-continuous extension of the Conley-Zehnder index. That in the 2n minus 1 dimensional case, this is that this number is at least n plus 1. So this is a their replacement of the convexity assumption, which is, of course, much more, goes back to, this is convexity is a setting where you can apply, calculus of variational methods, etc. But it's not a good thing when you want to do things symplectically. And this was their kind of replacement for this. So we know, of course, by now more about this condition. Convexity implies dynamically convexity. We did know, but we also know that the converse is not true. And let me also say that nowadays, this convexity assumption on the indices can also be quite weakened. You can get away with lesser things, particularly if you have a few more extra information in the picture. Okay, one way or another, it is pretty common assumption, and it will be the case in the results that I'm going to tell you today. Okay, so time to tell you about the results. So the first result will be on the multiplicity. So it pretty much is going to tell us that in the dynamically convex case, the conjecture holds. So if your Reeb flow is dynamically convex, then you have at least n prime closed orbits. The key thing maybe to emphasize here is that is that there is no non-degeneracy condition in this theorem. But we can say more if we assume that this is non-degenerate, the Reeb law is non-degenerate. For instance, if in this case, if you have a pseudo-rotation, then you can say that we have precisely n non-alternating prime closed orbits, and they have parity n+1, parity of convex index, or its lower semi-continuous extension here. The same as n+1, as I said. This is not quite new, the multiplicity part of it, but the last part is that precisely you have n non-alternating prime orbits with parity n+1 is probably new. The terminology of non-alternating also will, I'll be using this, at least in the statements of the theorems. This is something we are used to, of course. It's just that the number of real eigenvalues in the interval -1 to 0 is even. So the essence of this is, otherwise we call it alternating. The essence is, of course, whenever you are dealing with the multiplicity, you're going to have to deal with the iterated orbits, and this is about whether or not the convex index changes parity as you iterate.
Sorry, Basak, can I ask a question? Yeah. It's not clear to me what the when in addition means. Does it mean that if you have finitely many orbits, then you have exactly n of them and they are non-alternating, or you have n non-alternating and you could have more which are alternating? No, which one?
No, it says that if you have a it's okay, let me just repeat. So non-degenerate finitely many, so you have a pseudo rotation, then this number is precisely n non-alternating prime closed orbits.
So you have exactly n and they are non-alternating.
Exactly.
Okay.
With
thanks.
the same parity as n+1. Yes, this is exactly what it says. Yeah. And exactly, yeah. Okay, so let me. Okay, I'm just. I might have something wrong. So I am not saying that it is exactly n.
That's what not.
Yeah.
It's not clear from what is written. So that.
Yeah. Sorry. I got confused myself. So that's why I got. Yeah, but I'm just saying that there would be n non-alternating prime closed orbits. Like n of them will be with this property.
But there could be more.
That could be more. Yeah.
But the other ones would be alternating. Okay, thanks.
That could be, yes. I got confused, sorry. Okay, so let's go ahead. So, it's early. All right, so second result. So second result will be a case of along the lines of Reeb contact of Zoominar conjecture. And it's gonna say the following thing. So now I'm gonna again assume dynamically convex, but on top of it, I need to assume this time around, we assume non-degeneracy plus that the domain is centrally symmetric. In the sense of convex geometry, it is equal to negative of itself. Then we can say that you have n or infinitely many. So in other words, the n or infinity conjecture holds in the case if you have dynamic convex, non-degenerate, and symmetric hypersurface. Again, if in the case when it is n, you can say a bit more, say that all prime orbits are symmetric and non-alternating. Symmetric in the sense of x and negative x, x is invariant under the antipodal involution. Any questions about the results? Okay, so let me go ahead. So as I said already, these results are mainly of interest in higher dimensions, a dimension greater than 3. And the case of dimension 3, in terms of past results, we have almost everything we know that to infinity holds through the works of Hofer, Wysocki, Zander, Hutchings, Christopher Gardner, Ramos, Hirnevich, a lot of people. We know that the only three manifolds admitting pseudo-rotations are length spaces, essentially everything. And when you go to higher dimensions, also in dimension 3, we know, like not just for spheres, of course, for any contact manifold, we know a lot. When you go to higher dimensions, nothing like that as precise can be said beyond the case of spheres, at least when it comes to like lower bounds or any n or infinity conjecture, etc. So if you want to change your contact manifold, for instance, that would highly, this bounds would depend on the underlying contact manifold, etc. So from this point on, I'm going to focus on the multiplicity in higher dimensions. As I said before, if you don't assume anything, almost nothing is known in terms of index and non-degeneracy. And what we don't know is as basic as like, for instance, take S5, do we know at least more than one? In general, do we know at least more than two in the non-degenerate case? Now, the more studied, in terms of previous results, the more studied piece of this to conjecture is the lower bounds. So oftentimes, not oftentimes, essentially only with index or non-degeneracy requirements. For instance, the following were known. So some DC type condition plus non-degeneracy gives you at least n. The two together, let me emphasize. If you drop non-degeneracy here, this number drops to n-half. So our result is, for instance, improves it by half, n-half. And then if you assume lower dimensions like R4, R6, R8, etc., there are various results which gives you much more like precise statements, again, under all these conditions. So main credits here, a lot of the credit goes back to Long and his school here, all the way going back to his Long and Zhu's breakthrough work in 2002. Wang, Long, Liu, Wu-Tang Kang, more recently, of course, Miguel Abreu and Leonardo Maccarini, Victor with myself, we also have various results along these lines. And actually, I will try to describe how this proofs work, so it will give us an idea and, a bit later on. And then I can also think about multiplicity results for other manifolds, like unit cotangent bundles to spheres, unit tangent bundles to spheres. You can think about conic conjecture, contact conic conjecture type questions, and there are various results along these lines. And you can also think about the generic case of the conjecture, for instance, that C infinity generic, you would expect this number to be infinite, just like the case of in 3 dimensions. Now, what do we know about in terms of past results in the HC conjecture? So, of course, what we know mainly is in the Hamiltonian case here. So this story starts with, so let's for a second go to Hamiltonian world. We have a closed symplectic manifold and a Hamiltonian diffeomorphism. So this story starts with Frank's theorem. And so this is the 2-or infinity theorem for S2, holds for like area preserving diffeomorphisms of S2, but holds in more generality. And then it was conjectured by Hofer and Zander in their book that the same thing, a similar thing, works for should hold for CPN. Namely, this is the n+1 or infinity conjecture. This was proved by Shelukin so a few years ago. and even broader class of, or even a broader class of M's under some non-degenerate type conditions still. Still to this day, we don't know it in the full generality as it is, but these are, mild conditions at this stage. And an important key ingredient in Igor's proof is the symmetric inequality in Floer theory, going back to Zeidel's work and then Shelukin and Zhao's work. And this will also come up in our proof, as we will see. So I wanted to kind of bring up this whole thing. So we'll recall what that is. And then we also have other proofs for CPN, Simonale, and then more recently for toric manifolds, Bai and Shu also proved the Hofer-Zehnder conjecture like a year ago. So using totally different sort of methods like gauge lambda sigma models, I believe. And then there is, of course, another way to look at the HC conjecture. So let me advertise this a little bit too, because by itself, HC talks about just the number, but you could also think of it as in a different way. Perhaps it's not the number, but some other thing, like the existence of some out of place closed orbit forces the presence of infinitely many. Now, when you look at it in this more general sort of perspective a bit, I mean, previous results enter in this category. But you can also have other things. For instance, presence of hyperbolic orbit implies infinitely many, or similar results for non-contractible orbits. Along the lines of, again, a Hamiltonian diffeomorphism doesn't have to have a non-contractible periodic orbit, but if it has one, then you have infinitely many. So this is how you should regard this. Some results for symplectic morphisms as well when you look at it from this perspective. So maybe the result that I'm going to remind us is it's kind of sets the way for the next one in the Reeb case I'm going to say is a result about 10 years ago I and Victor proved, which is that for CPN, say for CPN, if you have a hyperbolic periodic orbit for a Hamiltonian diffeomorphism, then in fact you have infinitely many prime periodic orbits. So much the same way, when we enter the world of Reeb flows and the Reeb or contact of our Zehnder conjecture, like the one that I have stated in the beginning of my talk. So let me first, before I state our results with Arman, Victor, and Marco, one can ask, what do we know in the Reeb case? Essentially, almost nothing before 2023. So when you look at it like at most n or infinitely many, then one thing that one may think about is, of course, like upper bounds on the number of closed orbits also become relevant. So lower bounds is studied, but can you also say that this Reeb flow has at most that many? So some upper bounds were put for lacunary Reeb flows, so meaning that all closed Reeb orbits have the same index parity, were proved by, I proved under very restrictive assumptions again back in 2015, but more recently they were also studied for different set of manifolds like pre-quantization bundles, etc. by Avro and Maccarini. And beyond that, before 23, we didn't know anything about the Reeb case. And then in 23, we proved the following theorem with, again, Arman, Victor, and Marco. Marco was Ekeland. So we proved that on the standard contact sphere, if you have the dynamically convex Reeb flow, if there is one hyperbolic closed orbit, then in fact you have infinitely many prime closed orbits. So again, this has no non-degeneracy requirement. The actual index condition, as I said when I told you about dynamical convexity, is much more relaxed than DC. Actually, our condition implies DC, but it's milder. And now, maybe one thing that's gonna sort of one may ask at this stage, well, how is this related to your, what you're talking to us today, what I told you. And these theorems are independent. So the approach to proofs are independent. And I should say, rather interestingly, none of them implies the other one, actually. So these results I stated today and this animal are actually seem to live in different domains. And basically, in the contact HC world, these were the only two things, whatever I stated on this page, and the theorem B that I stated in the beginning. To the best of my knowledge, there is no other theorem along the lines of that tells you n or infinitely many, or presence of some specific type of orbit types infinitely many, this type of result. Okay, so now let me just tell you about how we approach the whole question and hopefully get to a little bit of the proofs. So what is the setting again? We are working with Reeb flows on the boundary of a starship domain. We have a ground field F. Now the choice of F in this business, in this matter, as you will see, is going to matter in some instances. When you need to use Smith inequality, for instance, it's proved for positive characteristics. And then if you work with, say, equivariant symplectic homology, then we know certain properties hold for over Q, zero characteristic, and doesn't hold in other characteristics. So you need to go back and forth a little bit, and luckily we have the universal coefficient theorem in most instances. This allows us to do that. But anyway, for now, we have, this is the setting. We have a background assumption. So I'm going to assume that all orbits, closed orbits, are isolated. So beyond some action threshold T, there are only finitely many with period less than T, period threshold or action threshold. Now, this is a purely, let's say, this is not an essential assumption, but it simplifies the matters when you work with persistence modules, etc. So this is not an essential thing. Maybe the thing to say is that the situations where we are going to care about, namely when you have finitely many prime orbits, or when you have something non-degenerate, such as the case in our theorem B, say, this assumption is satisfied. And then notation-wise, this is a non-equivariant symplectic homology in the interval negative infinity to T, SHT. And let's recall that this is this complex is generated, say, in the non-degenerate case. So you have one generator coming from the domain, interior of the domain, with this is of degree n with action 0. And then for each closed Reeb orbit with action less than T, you're going to have two generators. One will have the same index as X, and the other one 1 plus 1, and they will have the same action. And then this animal will be the, we are going to think of, put this graded vector spaces into this symplectic and the persistence homology language, and this will be the notation for that. So symplectic homology persistence modules comprising these Z-graded vector spaces, which are the filtered symplectic homology. So then if you put a closed orbit here, we have the non-equivariant local homology for a closed Reeb orbit, and then you have the S1 equivariant local symplectic homology of X, and this will be over Q all the time. So after this notation, so what is the kind of strategy of this proofs of these results? So one thing that is fundamentally different from a lot of the multiplicity results, which basically are based on this Dynamically type count, is that we're not trying to count. I mean, there will be some counting here too, but the focus of our focus is not counting distinct orbits using some kind of Morse theory or Floer theory. And what we are going to do rather is going to compare the persistence module with that of an irrational ellipsoid. Now, to this end, so let me say that if I forget, but I will repeat as needed in the rest of the talk, that just suppose that the Reeb flow is a pseudo-rotation, right? Which I can do in many instances, right? In all the theorems. So for the proof's purposes, one can assume that you have finite many prime closed orbits. So back to the strategy again. We want to look at this SHW for a dynamically convex Reeb pseudo-rotation, and we will compare it with ellipsoid, an irrational ellipsoid, and basically show that they are pretty much the same. Now, where does the motivation to do such a thing come from? Is because if you look at the examples of Reeb pseudo-rotations we have on the sphere, they're either irrational ellipsoids or those obtained via the usual standard conjugation method from ellipsoids, and therefore they have precisely the same fixed point data as that of irrational ellipsoids. And they're also DC, they're also non-degenerate, etc. So this is the world of examples. As far as I know, there are no other known pseudo-rotations or Reeb pseudo-rotations. So in fact, as an application, we will also see that when we assume like a non-resonance condition, we can also show that a DC non-degenerate Reeb pseudo-rotations, the fixed point data precisely matches that of an irrational ellipsoid. So they're actually pretty similar in that way. So you cannot, anyway, let me not say more at this stage. Of course, maybe the emphasis, one should also emphasize that they may have very different dynamics. Okay, so the situation of ellipsoid. So let's take an irrational ellipsoid here. So what we know is that all periodic orbits are non-degenerate, they have distinct actions, and the Conley-Zender indices are given precisely in this way, n plus 2i minus 1. They form this strictly increasing sequence. The orbits are ordered by index, and that this ratio is constant. And dimension of symplectic homology through with threshold t is 1. So through every t, we have precisely exactly 1 bar, basically, because this is going to measure like bars passing through t or containing t. So, and the picture is exactly like this. We have this ascending staircase with one riser corresponding to each of these periodic action value for these periodic orbits, closed Reeb orbits. The green ones are the ones coming from the interior of the domain. So here is the backbone of our argument. So the key theorem that all the proofs rely on is the following theorem. So call it theorem C. So let's say we have a dynamically convex Reeb pseudo-rotation on the boundary of a star-shaped domain, the setting we have. Then the statement is that exactly as in the case of ellipsoid, the dimension of symplectic homology for every t and for every ground field f is 1. So you have precisely 1 bar through every t in this persistence module. And again, there is no non-degenerate assumption in this. So what we will see is pretty much what follows from this is a corollary which is going to be used repeatedly together with this theorem. But before I state the corollary, let me introduce one more notation here, terminology here. So this is the terminology of F visible orbits. So we have our ground field F. We can look at the local symplectic homology for this orbit. And we're going to say that the closed Reeb orbit is F-visible if this local homology is non-zero. For instance, if you have a non-degenerate closed orbit, this is Q-visible if and only if it is a good orbit. So it's not an even iterate of an alternating orbit. Okay, so in the terminology, for instance, if all prime orbits are good. So Q-visible if and only if it's a good orbit. So maybe a few other things. Of course, you can also extend this notation to equivariant visibility, right? Just replace things with the equivariant homology. In that case, I'm only interested in the Q coefficient case. So something is equivariantly Q visible. In fact, it's if and only if Q visible. And something which is Q visible is always F visible by universal coefficient theorem. Another thing is the support of this local homology. The support is simply the degrees m where this homology is non-zero. Again, similarly for the CH. And the support is always contained in this interval of mu minus of x and mu plus, which is the upper semi-continuous extension of the lower semi-continuous index. So here is an immediate, essentially immediate corollary of theorem C, which said the dimension of SHT is 1 for every t. So the setting is exactly as in the previous theorem, a DC Reeb pseudo-rotation. First part says that all F visible orbits, so this set P of F, have distinct periods, and the dimension of local homology for all F visible orbits is local symplectic homology is 2. And the second thing that now concerns with Q coefficients, so SHQ is SHX is supported in 2 consecutive degrees. For all visible orbits, Q visible orbits, so this will be say H and H plus 1, and the equivariant homology will be Q only when index is H and 0 otherwise. Now, of course, I mean, why am I again using Q here? What goes into this, the argument, it will be important that the shift operator, which is the connecting map in the Gaussian sequence relating equivariant and non-equivariant homology, that in the local version of it, this operator is 0. It vanishes in the Gaussian sequence when the characteristic F is 0. And that's no longer the case if you don't work with positive characteristics. So and this is important for this case. And then you know that you can say that as a consequence that this local homology is just a direct sum of CH and CH with one shift to the left. So now, again, this essentially follows from theorem C, because in any other case, you would have to have more bars. For instance, to say phi I is true, you would have to have at least 4 bars through T. You would have to have a bigger dimension of SHT. So this kind of follows from theorem C. And the key thing about this is that this is going to allow us to assign a homological index to a closed orbit, which is visible. And then you see, when you don't assume non-degeneracy, one of the issues is like, what are we counting? What is index, etc. So this is going to allow us to associate a degree to an orbit. Let me go to my next slide. And this degree, by definition, will be precisely that integer while the equivariant homology is non-zero. So, but let me emphasize that I can only, this thing only makes sense if you have a DC pseudo-rotation plus visible Q visible orbits. So you do need this second part here. Okay, so now we have another theorem, which is going to be like the connection between this theorem C and theorem A and B, if you wish. It will tell us the following. Again, we are in the setting of theorem C. This theorem only concerns with Q coefficients. And we have the symplectic persistence homology module over Q, and we have the barcode of that persistence module. So then you can define this degree map. This degree map is a bijection from Q visible orbits to n-1 plus 2 times positive integers. And you have this strictly increasing situation, like orbits with larger degree have larger period. And likewise, you have this degree map from the bars from that from the barcode, so which will comprise bars in that persistence modules. Then this will have 1 less degree, and this will be a bijection, and bars with larger degree have larger period. Here, when I say the degree of a bar, it's really meant in the sense of persistence homology. When you write the whole thing, like using the structure theorem as a direct sum of interval modules, there will be this barcode coming from there, and they will know, to what degree they belong to. And the second part says that all closed Q visible orbits have precisely the same ratio of action to mean index. Okay, so let me try to look at the proofs of theorem B and A, and maybe this is going to be mainly theorem B. So again, let's recall that everything we are assuming that we are working with the Reeb pseudo-rotation. So I already told you a bit about the multiplicity in the DC non-degenerate case. So let's remember how this proof works. So the first lemma I want to say is the following. So DC non-degenerate pseudo-rotation has precisely n non-alternating prime orbits. So this comprises 3 steps. The first step is you use the so-called index recurrence theorem or index recurrence in the form. So that was like, there was the common jump theorem in the work of Lang and Xu, and then we have Victor and I proved, gave a different proof of it, and by now, actually, it has taken a much more sophisticated form, but for the purposes of, in the non-degenerate DC case, maybe you don't need much sophisticated forms. So it's basically a property about the recurrent properties of the Colmy-Zender index. So one way to state it would be that if you look at the derivative sequence, so mu of phi to the k minus k plus 1 minus mu of phi to the k minus 1, then this derivative sequence is going to repeat itself infinitely many times in the sequence of iterated indices. So you can apply it to one map or finitely many maps. So if we have time, I can say a bit more about this. But in the index recurrence and DC case, what does DC bias? DC bias that the first sort of recurrent situation is going to happen at least in n plus 1. So you need to go at least that much by this index lower bound. So it tells us that you have this index interval d minus n plus 1, d plus minus plus n minus 1, such that for every prime orbit, only sort of at most one iterate can enter this index range. Now, this d and ky exactly are in the statements of the index recurrence theorem. So this is kind of how this sequence that will repeat itself will repeat. So this is kind of the shift, basically. It's independent of the maps. And this is the iteration index. sort of order of iteration for a given prime orbit. So all what this is saying is that I have this index range where my prime class closed orbits can only sort of enter this range with only at most one iteration. That's it. Any other orbit will be outside the range. So here's the picture. So here's my range. The closed orbits are entering this picture at most, that many of them. And then the next iterations will start happening with at least this gap 2 here. Now, if you look at this range now, this range has exactly n integer points having parity n+1. And by using, again, spectral invariance Morse theory, Lustanich-Schneiderman theory would be the right one. So you have spectral invariance that needs to non-zero, that needs to happen exactly in these integer points with parity n+1, non-zero. So there must be closed orbits delivering these invariants. So therefore, you must have at least n of them. And they must also be non-alternating because, you know, they will give you non-zero equivariant homology, for example. And that, let me maybe go back and look at this part. This D can be chosen to be even. So the orbit has to be non-alternating to contribute, for example. So to fill in these spots. Now, you may ask, so what happens if you don't assume non-degeneracy? Basically, what happens is that because you don't have such a precise understanding of index and everything, so these iterations x to the ki's, ky's can only fill up like half the spots. By the other half can be filled up possibly other iterations of the same orbit. So only like this much can be filled up in an unambiguous way by spectral invariance. So this is that. We have this thing. Now enter theorem E. Theorem E tells us that, you know, these orbits have distinct indices, and then I have to have exactly n non-alternating prime orbits. So you see, I mean, I don't know, it's probably clear to you, but what would happen if you have one more orbit here? It would definitely have to have an index with parity n. And so I would have this odd orbit, even orbit, so to speak, and I would have to somehow cancel this orbit with something because I don't have homology in that degree, which has parity n. But to cancel that, I would have to have one more even orbit, one more orbit with parity n+1, which I don't have by the index recurrence theorem. So sort of these 3 stages of the proof, these must be filled, and you cannot have any more than that. So this is, let's see what we've done. We basically proved, we proved this lemma basically. Under these assumptions, you have precisely n non-alternating prime orbits. Again, possibly you can have more orbits. Now, let's go back to the proof of theorem B. So let me restate the theorem. A restatement of the theorem would be that if I have a pseudo rotation, which is DC non-degenerate, and if I also assume centrally symmetric domain, then I have precisely n prime closed orbits, and these orbits are symmetric and non-alternating. Well, there are 2 types of prime orbits in this case. These are either symmetric or asymmetric. So asymmetric guys come in pairs, yn minus y. Then, as I said, these are geometrically distinct, the one orbit and its antipodal involution. They have equal action and degree, but we have our corollary D or theorem E. This cannot happen because different, all these orbits, let me go back for a second for you, what this corollary D was. It tells us that all of these guys have distinct periods. So this helps us eliminate, sorry about back and forth, the asymmetric orbits. And then what remains is the symmetric guys. So x and minus x are the same bits. Then one can go back to the work of all the way along Zhu or Ginzburg-Maccarini, which tells us that in the non-degenerate, every non-degenerate prime symmetric orbit is actually non-alternating. And then lemma 1 tells me that there are exactly n such orbits. And that's kind of ends the proof of theorem B in this case. Now, theorem A is a part that I'm essentially not going to say much about. The thing is that what you need to do is you really need to look at the behavior of local homology under iterations, these guys. And this is a complicated, well-known complicated method. You really need to dig down into it, which we do, but it's kind of a bit beyond the scope of the talk. But you have some simplifications. We have results as we have our theorem C, corollary D, etc. So this the fact that the equivariant homology is supported in at most 1 degree sort of makes the whole thing somewhat more tractable. So
sorry to interrupt you again, Basak.
Go ahead.
Can you back? I somehow didn't understand what's complicated about SHYKF. I thought you said that that you have the Gizin sequence, and so SH and the certain map is 0, so you should be able to compute SH from CH, at least for rational coefficients. No? Is that correct, or did I miss that, or?
Hold on, no. Just a second. For rational coefficients, yes. Yes.
And why do you need non-rational coefficients?
Well, because you need things such as Smith inequality, for example. And this works for positive coefficients.
So the complication comes from the fact that you want to compute this for f in a different field than the rational.
Yeah.
If it was just, but if it was just the rational, it would be obvious, no?
If it were just, I mean, if you knew things, well, that is not true, I suppose. I think so, yes.
Okay, thanks. Sorry for
so. Yeah. No, that's fine. I'm
sorry for interrupting.
No problem. No, it's really, we do need to work with this go back and forth has to happen in between rational characteristic 0 and positive characteristic. Yeah.
But so far, sorry again. But so far you didn't mention Smith.
No, I haven't gotten to the proof
you didn't
of
say
the
where.
backbone. I haven't gotten to the proof of theorem C yet. That the dimension of symplectic homology is 1.
But that's for any field?
Yes, that's for any field. For any field in any field F, yes.
And it's not enough to have it for rational coefficients. Okay, I'll stop interrupting you. Go. I'll ask questions at the end.
Yeah, okay. So let me quickly pass through this slide. So I already mentioned the ellipsoid comparison. Maybe I want to say a bit more about the proof of theorem. So, but nonetheless, let me, given that I already mentioned it, with the proof strategy, I already told you one can ask like how similar exactly a Reeb pseudo-rotation to an irrational ellipsoid. And here's basically a corollary. Maybe let me not. So this is like a corollary which uses the entire package, all the way theorems A through E that I listed above. So in the setting where non-degenerate DC exactly unprime orbits, which are all non-alternating. So this is a situation where, when say, if you have a symmetric hypersurface, these things hold by theorem B in that case, these conditions. If you also have a non-resonance condition, you can show that for every such Reeb pseudo-rotation, there is actually a matching ellipsoid, an irrational ellipsoid, with precisely, in other words, exactly the same periodic orbit data. So what, in particular, all orbits, all closed orbits in this case will have to be elliptic. So, but we also know at the same time that dynamics on the boundary can be dramatically different, right? We can have very simple integrable situation in ellipsoids, and then, or at the same time, we can have like ergodic dynamics, even in the situation of our theorem corollary F under all these conditions. So one sort of interesting question here is, well, this basically tells us this, the symplectic persistence. I mean, they will have the same symplectic homology persistence module, all the same symplectic homology info. So it obviously doesn't tell us anything about the dynamics on the boundary. And one can just ask how much of the dynamics does the interior see on the boundary, basically. So we know that in this case, the closed domains are not, say, symplectomorphic, but can the interiors be symplectomorphic still in these cases? So these are kind of, I wanted to bring up as it's kind of interesting. So let me go back to say a few words about the proof of theorem C. So this proof, again, what we are trying to prove is dimension SHT is equal to 1 for every field for every T. So there are three main ingredients here. One of them is the boundary depth upper bound, which says that if the total symplectic homology is 0, then the boundary depth, the largest bar, is bounded about by some constant. So, and this is 0 in our case, for instance, if we have a star-shaped domain in our end. In the displaceable case, the fact that this is 0 goes back to Claude's work from 99, and then in general it was proved by Chilebag, Van Vandel, and Oancha. So this is number one. Second thing is Smith inequality. Again, going back to Seidel and then Shelukin and Zhao, which was important in Shelukin's proof of the Hofer-Zener conjecture. It tells us that this dimension, let me maybe look at the case that we are going to use more, dimension of for PT threshold SH is at least the dimension of SHT, basically. So you take this interval multiplied P, so by P enlarge it, so it's going to be, this dimension will be greater or equal to. And then the next ingredient, as I already told you, is index recurrence. So this recurrence properties of Cohen-Zender index. So this is not really like symplectic topological result. This is about geometry of numbers, combinatorics, linear algebra, if you wish. But the new version that we however need a much more sophisticated version here, and this incorporates not only the indices but also actions and frequently of how frequent these repetitions are going to happen. So this is like the last ingredient. So, and this ingredient, index recurrence, in the dynamically convex case, is like all over the proof. It is used very much. Okay, so now the outline of proof. I know I have little time, but maybe I'll have a few more minutes extra. So, okay, so let me set dt to be this dimension. We are going to prove this theorem only for positive characteristic. Again, the result will be true for by the universal coefficient theorem for any field. The first proposition here is I claim that there is a real sequence CL going to infinity with bounded gap. such that this dimension is at most 1. Now let's try to obtain theorem C from this. Well, symmetric equality tells me that this dimension is at least 1. Indeed, if you go to symmetric equality and apply it, you divide p to the k with one side, this side will be t. And now if your k is large, this is going to be so small, so this is only going to capture what's coming from the interior. So therefore, this will be 1. And therefore, we get this. Now, again, by the same symmetric inequality, you can find arbitrary large action intervals such that the dimension of SHT is less or equal dimension of the SH tau for every tau in this interval. Indeed, let's take an interval. So this won't be my I, will be this t plus epsilon, which doesn't intersect our the spectrum of all periods, and then just multiply the whole thing by p to the k, and we are here. So we get this, and finally, given t. So remember, I'm trying to use prop 1 to obtain theorem C. So given a positive t, I can find a CL in this interval because this is a bounded gap sequence, so it's going to intersect these intervals. So I can find someone there. And then using what I have about, the d tau for anyone in this interval will be less than dCL, and this is less or equal to 1 by proposition 1. And now I have this, that tells me that this is 1. So I need to prove this thing. So of course I don't want to prove this thing, so let me introduce another proposition, which is going to imply the first one. So the second one, which tells me that I can find a sequence, real sequence CL going to infinity, again with bounded gap, so that the symplectic homology, filtered symplectic homology with this filtration CLs, is 0 whenever the degrees are have the same parity as n plus 1. So how does this imply proposition 1? Well, let's set an Euler characteristic here for symplectic homology. Well, this thing is actually independent of t. And because each one of them, as you pass through critical values, will come with 2 generators, which have exactly the opposite parity. So this will come from, again, your interior of the domain. So this will be independent of t. Now, what is DCL? DCL is precisely the sum of dimension of symplectic homology, filtered homology in these degrees with this action threshold. Now, proposition 2 told me that, what did proposition? This is, oh yeah, proposition 2 is here, sorry. So you see this thing is 0 when they have index parity n plus 1. So just plug everything into this formula. This thing will spit out. What remains here will, from this formula, what remains here will be precisely the dimension DCL. And then I will just conclude that this is equal to 1. Okay, so this is kind of now what we need to show. Okay. Okay, I'm already sort of outside my time, but I have very few slides. Let me go through briefly explaining to you how that works. So here's what you do, several steps of this proposition. So to every bar, I can assign visible closed orbits. Let me call this beginning of the bar and the end of the bar. Okay, so this orbit will have precisely the same action value as the beginning of the bar. And the degree of the bar will be in the support of the local symplectic homology for this orbit. So this one can this is not a difficult thing to do. One can do this in a kind of nicely. Now you take your visible orbits, break them into clusters. They will enter into the same cluster if they have precisely the same ratio. And because we are assuming finitely many orbits, we have finitely many clusters. Let's label them such that I will denote the cluster, and then in this cluster there will be other guys. So this J will be these guys, and K is for the iterated orbits of these prime orbits. Now there comes lemma 2, which is again essentially follows from the boundary depth upper bound, which will tell us that beyond some action threshold, so if your beginning value is beyond bigger than this, in fact, you're not going to have intercluster bars. In other words, you have these clusters, but only bars you're going to have will be within the same cluster, and that's it. If your bar has bigger than this constant, so this action threshold. So that's not a difficult thing to show using the boundary depth upper bound. Now, the next thing is DC plus together with index recurrence will tell me that you can have these bounded gap sequences. And again, these even integer sequences such that for all J and K, if your action is to the left of this yellow line, this CL, then the upper indices will satisfy this inequality. If you're to the right of it, they will satisfy this inequality. We will apply this when I is the same shortly to finish the proof. Promise this is the finished end of the proof. So this, what is this dt? It just counts the number of bars containing T, passing through T. So let's take a bar passing through CL, but I want to pick this CL. Remember, this is a bounded sequence going to infinity. I want to pick this CL, which is greater than the boundary depth upper bound plus this K bar that came from my second lemma, which told us that beyond which you don't have any intercluster bars. So with beginning Yijk and ending Yij prime K prime, these I's are the same by lemma 2. And notice that beginning of this guy will have action less than CL and the end will have action bigger than CL, which is precisely when I can apply these guys. So then again, by looking at simply what the degree of a bar in connection with the beginning and the end maps, etc., I will have precisely this situation. This difference must be less than or equal to 2. And so above, and this is the maximum, these things are actually have to be equalities, and this difference must be precisely 2. So here's this picture where these homology are supported. These are the limits of the higher limit for this guy and the lower limit in this for this guy. And so this is the only bar you can have, basically. So it tells me this is precisely that. Let's remember that these guys are even. So this is exactly what I wanted to prove, that this is supported in degrees precisely the same parity as n. So in other words, this is 0 when the star is n plus 1. So let me stop here. Thank you.
Thank you very much.
I'm sorry for going over time.
So please ask questions if you want. I can look if anyone is raising a hand, but go ahead. So there were already many questions during your talk, but okay. All right. So
I confuse everyone fairly well.
Yeah, I can ask a question. Hi, Basak. Do you see any way to extend this to pre-quantization bundles?
Well, I mean, yeah. This argument as it is, maybe not. I mean, you will need all these ingredients for that. So if you can prove similar things, you could, I suppose. That would be my guess. But as it is, I don't think like readily you can apply it to pre-quantization bundles.
No, sure, of course, as it is not. But like, do you think it's like impossible, or that it would just by modifying slightly the argument it would go through? That was some other question.
It could go. I mean, I think it could go through. But I'm just trying to kind of. But again, I mean, that would be. I mean, that would be a case to look at, obviously. That's, I guess, what I want to say. Yeah.
Maybe let me chip in here. So I think it has a chance of going through for pre-quantization bundles, except the dynamical convexity condition does not make much sense. I think there is one key ingredient which is missing, and this is like an a priori bound on the boundary depth.
Exactly. Yeah. Exactly.
But outside the sort of the only pre-quantization bundle I can think of for which dynamical convexity would make sense sometimes is the unit tangent bundle of the sphere. And this is, of course, like the most interesting case.
Of course, yeah.
More interesting than the case we do. But even then, the dynamical convexity is actually a curvature restriction for the metric. So kind of, it has a chance. My answer would be it has a chance of going through sometimes if you fill in the ingredient, but there are very few interesting cases. So that's kind of how we think about it.
Okay, thanks.
But your case is the pre-quantization of CPN.
Yes.
Yes.
Yes, and this is like the easiest case. Yes, our case is.
But maybe you need that the base has a perfect Morse function, something like that, so that you don't have interference between the critical points of the given by the circle and the critical points coming from the base. So maybe if the base has only even homology, something like that, maybe it's easier.
Yeah, it's fine, Claude, but we really use dynamical convexity. And in most interesting examples, it will never, the condition as is will never be satisfied. So if you are, it will be very rare. Sort of the homology of symplectic homology will be usually non-zero in degrees below n.
But you can imagine of changing the condition to say, okay, you don't have orbits, like you have the homology starting in some positive degree, and you just say the condition on index is that you have no orbit of lower index than that rank, where the homology is non-zero.
And then the argument will completely break down. This n plus 1, the relation, the fact that n plus 1 is the dimension is important. Like the interplay between this gap in homology and its relation to the dimension is extremely important.
Yes.
Okay.
Beautiful result anyway. It's great.
Thank
you. So thank you very much. I don't know if there are more questions. I don't see any, but in any case, thank you very much, Basak, for really
well,
beautiful
thanks for
talk
inviting me.
and for very interesting. It's an amazing type of accumulation of results, and